let's see, today we're going to be looking at properties of imaginary numbers. When we're done with this, we're going to be able to say, I can simplify imaginary numbers. So previously we have gone through and defined an imaginary number I as I times I is -1, or I is equal to the square root of -1. So it has some interesting properties as we go through and deal with these. Okay, so looking at these things here, if I go through and say, hey, what is I to the first power? First power here. Well, that's just going to be I to the second power, well, that was our I times I, which we know by definition, this is -1. That's our definition. Okay. I to the third power means to do I times I times I, which if you look at this right here, these two together make -1. So therefore I say -1 times I, which makes -I. And then this last one here I have I times I times I times I, which these two together here and these two together here, this gives me -1 times -1, which -1 times -1 gives me +1. Okay? So, some interesting little properties with this. Notice there are 4 things here. I like to think of it just like you would 4 quarters in a dollar. Okay? If you have 1 quarter, that's going to give us I. 2 quarters would give us -1. 3 quarters is a -I, and 4 quarters, that's a whole dollar, so that's 1, a +1. So let's look at how we actually can use that. Because I could go through and write out I 11 times and work that out just like we did the previous examples, but that gets to be a lot of I's to keep up with. And I don't want to do that. So what I'm going to do is I'm going to take this exponent, 11, and I'm going to divide it by 4. And if I do 11 divided by 4, that's going to give me 2.75. And at this point, I'm going to look at that and say, hey, that's 3 quarters. 75 cents is 3 quarters. 3 quarters tells me that it is -I. And we can do that with every one of the problems. You take your exponent and divide it by 4, and whatever the remainder is tells us where it's going to fit. So looking at our next example here, I'm going to do 30 divided by 4, and that one would be 7.5. That's 50 cents. 50 cents is 2 quarters. 2 quarters is our definition, which is -1. Anytime you have any of these problems, you take your exponent, you divide it by 4, and depending on what the remainder is, that's where it's going to fit. It's either going to be I, -1, -I, or +1. So suppose I gave you one that was like I to the 147th power. And I said, hey, what does that one simplify to? Well, I'm going to do 147 divided by 4. I can get out a calculator there and punch that in. And I see that it's 6.75. Oh, 0.75. That would be 75 cents. 3 quarters. 3 quarters is -I. Okay? Does that make sense? We're going along, whatever it is, we take in, divide it by 4. Look and see what the remainder is. Suppose I have one like this, says I to the 624th power. So I do 624 divided by 4. 624 divided by 4. And I get that one is 156. There is no remainder for this one, no decimal. That means it's a whole dollar. If it's a whole dollar, that's 4 quarters. 4 quarters is 1. It doesn't matter how large the exponent is. Every time, just go through and divide by 4. And what your remainder is will tell us which one of these 4 choices there will be. Now we can also do other things with our imaginary numbers. Okay? So adding and subtracting imaginary numbers is the same thing we would do if it was like treated like a variable. We're just going to go through and collect like terms. So looking at this one right here, it says negative 6 minus 2i plus 2 minus 7i. Well, if I go and just collect my like terms, I got negative 6 and a positive 2. I put those together, making a negative 4. Then I'm going to collect up my negative 2i and my negative 7i. And negative 2 and negative 7 give me a negative 9i. And at this point, that's all we can do with it. Okay? Just collecting like terms, just like it was if it was a variable. Looking over here at this example, collect up my real portion of my number. Now these numbers together like this are what we call complex numbers because they have a real portion and an imaginary portion. Complex numbers. So our complex numbers have a real portion A plus some imaginary portion such as BI. So 5 plus 6 is 11. Then I collect up my imaginary portion. Positive 6 and negative 5. Put those together gives me a positive 1i, or just I. Remember, with variables we do not put the ones in front of them. They're understood to be there. Okay? Now when we go through and do subtraction, we got to remember, oh, I have to distribute this minus sign into everything behind it. So I'm going to rewrite the problem. So I have 3 minus 4i to start with. A negative and a negative makes this a plus 5. A negative and a positive makes that a minus 7i. And at this point, I can go and collect my like terms. 3 and 5 gives me 8. Negative 4 and negative 7 is a minus 11i. So when we're dealing with subtraction, don't forget to distribute. Think of it as this is like a negative 1 times everything in the parentheses behind it. Looking at another example like that one. Here, I'm going to take and simplify this right here, distribute it into here. So rewriting the problem, I got my 5 plus 3i chilling at the front, waiting to see what happens. A negative and a negative makes that a plus 2. A negative and a negative makes that a plus 5i. Collect the like terms, so our real portion, 5 plus 2 gives me 7. 3 plus 5 gives me 8 with the I. Adding and subtracting our complex numbers, our imaginary numbers. So keeping in that same vein, so we have done some adding We have done some dealing with some exponents with our eyes, so let's go and see what else we can do. We can do multiplying. It says here, hey, I can multiply imaginary numbers, which we know by definition. We've already done this, talked about it earlier. Here's my definitions of what I is, and we're going to be multiplying our complex numbers. So when we multiply our complex numbers, we got to remember that if we ever get I squared, we have to simplify that. That becomes -1. Okay? So when we go to multiply these, we can either use our box method for multiplication, or we can use FOIL. Pick whichever one you like to work with better, and just go through and work it out. Let's do the box method with this one. I'm going to put 3 and 2i up top, 1 and 7i here. We go fill in our box. I'll do 1 times 3 is 3. 1 times 2i is 2i. 7i times 3 is 21i. 7i times 2i is 14i squared. So if I go and collect my like terms, I have 3. These two are like terms right here diagonally. So it'd be plus 23i plus 14i squared. But remember, anytime we have I squared, we can't leave it like that. We have to simplify it. So this is really 3 plus 23i. This is 14 times -1. So that'll be minus 14. And now I can collect the like terms with this, because -14 and the positive 3 are like terms now. So my final answer would be -11 plus 23i. When we write our complex numbers, always make sure that you put the real portion first and then the imaginary second. So let's look at another example here. This one says, hey, I'm going to want to multiply 1 plus I to the second power. So what this really means is I want to do 1 plus I times 1 plus I. And for this one, we're going to wrap our baked potato and use some foil. Because we cook baked potatoes, we wrap them in foil and throw them in the oven.
I love baked potatoes.
Get them all hooked up nice and yummy. So I'm going to multiply my first. My first is 1 times 1. 1 times 1, that's 1. Then I multiply the outers, the outside pieces. That's 1 times I. 1 times I is I. Then I multiply the inside. That's these two pieces here. I times 1, which is I. And then I'm going to multiply my last, which is I times I, or I squared. So plugging away at that, I hope squared, don't forget my square there. And we go through and we collect our like terms. So I got 1 plus 2i plus, oh, remember we can't leave this like this. This really becomes a -1. Now my -1 and 1 cancel each other out, so my final answer is 2i. Don't forget, anytime that you have an I I squared, you have to simplify. So we've been multiplying regular binomials, but we're going to multiply these by what we call the complex conjugates. Now when we multiply with complex conjugates, that's going to give us a real number for our final answer. So looking at this, here I have 5 plus 3i and 5 minus 3i. These are complex conjugates because they're exactly the same, but I got a plus and a minus. The only difference in them. So, using FOIL to multiply, I'm going to multiply my first two pieces, 5 times 5. 5 times 5 gives me 25. Multiply the outsides, 5 and negative 3i gives me negative 15i. Multiplying the insides, and I have 3 times 15 is a plus 15i. And then after that, multiply the last. 3 times negative 3 is a negative 9i squared. Notice our middle terms here are opposites of each other and they will eliminate. I have my 25 chilling out front, minus 9 times negative 1, because I squared is negative 1, because don't forget, we always simplify our I squares. So I have 25 plus 9, 25 plus 9 is 34. Multiplying with the complex conjugate gives us a nice, pretty, real number. And these come in handy when we have to rationalize denominators and do some other activities with them in solving equations. Multiplying imaginary numbers, simplifying exponents, collecting like terms. Imaginary numbers. They're a lot of fun.